Welcome back to part 3 of my data logger project. It's been real. I finally got all the pieces put together and the software written. The good news is it actually works as expected. My goal was to create a graph of domestic water pressure readings over time. Any variables that are available as 0 to 5 volt analog signals could be logged using this approach. Temperature and humidity are examples. This video is for those who enjoy tinkering with microprocessors, software, and building stuff. Those people usually enjoy seeing what others are doing. This project is my solution, but certainly not the only solution. When in college, I studied computer science as it was called back then. Here's a study session from 1978. You'll notice punch cards, dial phone, green stripe paper, and a magnetic tape cartridge. I worked in a computer graphics lab, and we had a state-of-the-art IMLAC graphics computer which had an 8K core memory, 8-inch floppy disk drive, and CRT display. You could program it in PDP-8 assembly language and Fortran. A 200-line Fortran program would take 45 minutes to compile. We were studying algorithms that could figure out which lines on a cube would be hidden. Intel offered its 8080 microprocessor chipset to students for $50. As for PCs, it was the S100 CPM system with an assembler, WordStar, DBase 2, and 64K of memory, all running at 4 MHz. Fast forward the tape. The advancements in hardware and software technology are staggering. As designers, we have access to incredible building blocks. Costs have come way down and capability has advanced in ways no one thought possible. The Arduino and Raspberry Pi microprocessor products are good examples of affordable, robust platforms. These are directed at hobbyists and education, not industrial strength applications. Let's zoom in on how this affects their usage. Industrial environments usually contain noise in the form of voltage spikes, RFI, EMI, ESD, lighting, motors, welding equipment, relays, contactors, and power systems, to name a few. These can cause potential problems for sensitive microprocessor applications if precautions aren't taken. As for the Arduino NANO V3 PCB, its processor pins come directly out on the male headers. This allows flexibility with pin functions, but exposes the processor directly to potential damage from noise. Source and sinking currents are usually low for processor pins. Voltages are also limited to VCC, which is 5 volts for the Nano V3. For example, a 12 volt 100 milliamp relay coil can't be directly coupled. If you know in advance the pin functions required in your application, interface circuitry can be added to the processor pins. This will elevate the Nano V3 or other SBC to industrial duty. The PCB I designed has 4 buffered DOs, 4 opto-isolated DIs, and an RS-485 4-wire COM link. I use the native processor pins INT0, INT1, and 2 analog inputs to complete the package. The Nano V3 is a slave device which reads the pressure sensor, rotary encoder, and manages the LCD. Since it lacks file storage, the master laptop commands the pressure readings to be passed back via an RS-485 link. The laptop controls the reading interval, timestamps the pressure values, and creates the CSV file. The file is easily copied to a USB thumb drive and imported into a spreadsheet tool for graphing. There is a link in the description to a circuit diagram for the PCB. The old Dell laptops can live again with Linux Mint 20.3 and offer inexpensive capabilities. In the next video, I'll go into the Dell hardware, software, RS-485 link, CSV file, and how to generate a nice graph of real data. I hope you've enjoyed this project so far. Thanks for watching.